this module, we continue our discussion of frequency response analysis. In the previous two modules, we introduced frequency response as a basic concept, and we learned how to sketch Bode diagrams by hand. In this module, we will continue our discussion of frequency response analysis, and we will discuss two topics in depth. One is using frequency response to assess stability, and the other is using frequency response data to do system identification, in other words, to generate black box models. So we've discussed stability previously in the course, and we've defined stability by the real part of the closed loop poles having negative real part. Graphically, that means that the poles are in the left half of the complex S-plane. Beyond just assessing stability, we would also like to assess relative stability. How stable is the system? Because when we design our system and design our controllers, we may have limited knowledge of the disturbances and noise, we may have limited knowledge of the plant, and so our estimate of where the closed loop poles are may be incorrect. And so we don't just want to be stable, we want to be robustly stable. We want to have some margin so that if we were incorrect in our analysis, that the system remains stable. And so one way to assess relative stability is how close are we to crossing into the right half plane, because poles with positive real part have exponential growth indicating instability. So the farther we are away from the vertical imaginary axis, the more stable we are. It turns out the frequency response of a system can also give us information about relative stability. In fact, it can give us more information than just looking at the poles of the system. So specifically, the stability of a closed loop system can be determined from the system's open loop frequency response. And at this point, I'm going to try and give a sort of a hand-waving, intuitive explanation for why this is the case. So recall, with frequency response analysis, we feed our system sinusoids of different frequencies. And so let's say that we give our closed loop system a reference sinusoidal input, and that signal goes through the open loop and is fed back here at this summing junction. And so going through the open loop system, the sinusoidal input to that open loop system will be scaled and shifted as compared to the input sinusoid in steady state. So we put in a sinusoid of one frequency. Once it goes through the loop, we'll also have a sinusoid of the same frequency, but it may be scaled, it may be amplified or attenuated, and it may be shifted in time. So for example, the time at which the peak of the input signal will be at a different time to where the peak of the signal is once it goes through the open loop system. And so when we do that, we get ourselves into trouble when the open loop system shifts the signal by 180 degrees. When it shifts the signal by 180 degrees, the output, or the signal that's about to be fed back, is exactly out of phase with the reference signal. So at a time instant when the reference is at its peak, the feedback signal will be at a valley, and when the reference signal is at a valley, the feedback signal will be at a peak. And so you can sort of imagine, we have our reference and we have our signal that's being fed back, and it's completely out of phase. So we get something like that. If we were to simply add those two signals, we get what's called destructive interference. This is -1, it adds to +1, so the sum is just 0. But in this case, we're not simply adding the feedback signal to the reference. We have a negative feedback system, so we're subtracting them. So when we do the subtraction, in essence we get constructive interference. We have that the reference and the feedback signal are lining up and being added together, because of the subtraction. And so when you get constructive interference, the amplitudes in essence add, and so you get a signal at this point that has an amplitude that is the sum of the amplitude of the reference and the feedback signal. Seeing that, you can start to get a feel for how that might be bad. You're adding signals and their amplitudes are getting larger and larger and larger. So being out of phase seems to be a problem or something to be concerned about, but it really only becomes a concern when the open loop system is amplifying the signal. So if we're doing this summation here, we're doing this constructive interference, but the open loop system is attenuating that signal, then that's okay. But where we get into trouble is when we're getting this constructive interference, but then the open loop system is amplifying the signal. So we add, we amplify, we add, we amplify, we add, we amplify, and the output of the system then blows up. We get an unstable system. And this is something that you may have a feel for. You can imagine a situation in an auditorium where you have a microphone and a speaker, and the output of the speaker is getting picked up by the microphone, and you get this feedback loop, and you hear this awful screeching where the amplifier is being saturated, basically because you get this unstable feedback loop happening. So the intuition here is like that. And so to put this into words, when the open loop system has 180 degrees of phase lag, the reference and the feedback signal add, we get constructive interference. And if the magnitude of the loop is greater than 1, if the open loop system is amplifying the signal, then the error grows exponentially and we get instability. So hopefully that gives you a little bit of intuition. To be more precise, we want to have a measure of relative stability. We want to know how far away is the system from becoming unstable. And so previously we had looked at how close the poles are to crossing over into the right half plane. In the case of doing a frequency response analysis, we want to know how far away is the open loop frequency response from the point that we have 180 degrees of phase lag and a magnitude of 1. So how far away are we from the point at which we get out of phase and then we amplify that constructive interference? Specifically, we're going to break this notion of relative stability down into two quantities. One quantity we'll call the gain margin, which is how far away the system is from the point of amplification. So how far away is the magnitude plot from the point at which we go from attenuation to amplification, that being a scaling of 1, at the frequency where we're 180 degrees out of phase. So when we're 180 degrees out of phase, how much gain can we increase before we start to amplify? The second quantity is phase margin. And so at the point at which we have a magnitude of 1, at the point at which we've gone from attenuation to amplification, how far away is the phase from the point of being out of phase? How far away are we from the phase being 180 degrees or minus 180 degrees or any multiple of 360 added to that? And so these two quantities are very important and we're going to use them a lot. And on the next page I'll show a picture to help you try and start to become more comfortable with these concepts. So as stated on the previous slide, the gain margin is this quantity here. So when the system is out of phase, so when the system is at a phase of minus 180 degrees, so this at this frequency, we call this the phase crossover frequency. So at a frequency where we're 180 degrees out of phase, how far away is the system from going from attenuation to amplification? So here the magnitude plot is below 0 dBs, where 0 dBs corresponds to a scaling of 1. So here we're attenuating the system because we're below the 0 dB line. So how much gain can we add before we reach this point of amplification? So this is the definition of gain margin. Similarly, we can look at phase margin, and that's this quantity here. And at this frequency, the frequency at which we're at 0 dBs, we call this the gain crossover frequency. So at this point where we have a scaling exactly equal to 1, how far away is the system from getting out of phase? So how close are we to the minus 180 degree point? So this defines our phase margin. So looking at this, the vast majority of systems have this sort of shape, where the magnitude decays, attenuates at higher frequencies, where the phase gets more negative at higher frequencies. In those situations, these definitions of phase margin and gain margin work very well. However, if we have a situation where we have multiple crossover frequencies, where the magnitude is crossing back and forth across 0 dBs, or the phase is crossing back and forth across minus 180 degrees, or we have a higher order system or a non-minimum phase system where we have a large range of phase lag, so that we're not necessarily at minus 180 degrees, we're at 180 degrees or 540 degrees, then these definitions and the Bode plot in general isn't the best way to assess relative stability. In that case, it turns out that it's better to employ the Nyquist plot and something called the Nyquist stability criterion. And so we're not going to get into that here, but it's something to keep in mind if you do some more advanced study, or if you come across some sort of more complicated systems that need to be analyzed. But for this sort of typical system, which we'll see the vast majority of the time, these definitions work well. And in order for us to say that our system is stable, we need to have both positive gain and phase margin. So our gain, our magnitude, needs to be below 0 dBs when we're minus 180 degrees out of phase, and our phase needs to be above minus 180 degrees when our magnitude is at 0 dBs. A little bit more intuitive way to think about what gain margin and phase margin represent is this. So gain margin indicates how much we can increase the loop gain before the system goes unstable. So for example, let's say that this Bode plot represents our open loop system. So we have some closed loop system, and this is the Bode plot of the open loop portion of the system. If we change the loop gain, or we add additional gain into our open loop system, that's going to change the frequency response, the Bode diagram of the open loop. Stop and think back to what the effect of adding this gain k would be to our frequency response plots. So if you recall, the Bode magnitude plot of a simple gain is simply a straight line equal to 20 log k. And as long as k is positive, its phase is always 0 degrees. So if we added this k, that's what the Bode plot of that magnitude component would look like. Also recall that when we have components in series, their Bode plots just add. So if this is our original system with this blue line and we add this k, then we're going to add a straight line to the magnitude plot of magnitude 20 log k. So the magnitude plot would look exactly the same, except it would be shifted up by the amount 20 log k due to the addition of that gain. And the phase plot would be unchanged, because the phase plot of a simple gain is simply 0. And so you can see that as we add this gain k, as we increase the value of this loop gain, we eat into our gain margin. And so the gain margin is an indication of how much loop gain we can add before we go from attenuation to amplification and our system becomes unstable. So that's one interpretation of the gain margin. It indicates how much we can increase the loop gain before the system goes unstable. Phase margin, on the other hand, indicates how much phase lag we can add to the system before it goes unstable. And the most likely source of this phase lag is time delay. And that's something that we haven't talked about in detail, but we will discuss it in subsequent modules.